大家好。
Good morning, everyone. My name is Koyashi. My topic is flow visualization and analysis flow using different helix structure. Extraction is a method employed to enhance purity, involving the mixing of two immiscible liquids without the need for heating or friction membrane. Our laboratory previously developed the core annular liquid micro extractor. It has adjustable helix wire establish a stable interface between the immiscible liquids. And the previous experiment involving toluene acetone water extraction revealed superior performance in smaller gap helix wire. A CFD simulation confirmed that smaller gap generate voltage, thereby enhancing heat and mass transfer. Our objective is to expand the gap size while preserving the voltage to optimize the CALLNE system. In this study, liquid interface within the gap of the helix wire for the transfer of substance. The formation of the liquid interface is governed by the interplay of surface tension, Laplace pressure, capillary effect, and pressure drop. The surface tension between the two liquid phases results in a pressure difference, known as Laplace pressure, which influences the interface by causing an imbalance of internal and external pressures. The pressure drop arises from the friction between the liquid and the channel. In our experimental setup, which employs a closed flow system, there are separate pressure drops for the aqueous and the organic phases. For equilibrium at the liquid interface, the Laplace pressure must exceed the total pressure drop to maintain the internal fluid within the helix wire. Our research focuses on analyzing the flow pattern within circular and square helix wire configurations, which observing variation in vortex formation within the gap. We maintain a consistent liquid contact area while alternating flow rate and gap width, ensuring both wires had an equivalent circumference. The simulation models were developed using Thomson multiphase, involving helix wires made of 304 stainless steel with a diameter of 0.15 millimeters. The investigation centers on the internal fluid, hence the outer flow rate of toluene is set to 0. For the simulation result, when flow rate fixed at 1000 microliter per minute, when gap width of 19 micron, there are a large vortex in the gap, and as the gap width increases to 150 microns, the large vortex will split into two smaller ones. Finally, at the gap width of 180 microns, the vortex are not generated. When the gap width is 120 micron, the shape of the vortex remains relatively unaffected regardless of the flow rate. Comparatively, change the gap wise has a more pronounced impact on the vortex shape than altering the flow rate. The result of square and circular head wires is heavily similar. However, due to the configuration with fixed equal circumference, the cross-sectional areas of the channel differs. This results in higher internal fluid velocity in square head wires. From the preceding result, it shows that gap wires played a significant role in determining vortex shape. Hence, we conduct a series of tests with varying gap wires, categorizing vortex as perfect, effective, or invalid. An effective vortex is defined as one where the vortex area exceeds the half of the gap wires. When we maintain the gap wide to 90 to 150 micron, we can make a vortex existent. To delve deeper into the numerical values near the liquid interface, we will record the scalar quantities of velocity and vorticity within the 5 micron distance of the interface. At the gap width of 19 micron, velocity increases with the rising aircraft flow rate, exhibiting a significant surge at the center of the gap. The variation in velocity is minimized at the flow rate of 100 microliter per minute. When the aircraft flow rate is 1000 microliter per minute and the gap width is 180 micron, there is a notable increase the velocity at the center of the gap. For the gap width of 120 and 150 micron, the variations in velocity are similar. However, the 150 micron gap displays slightly higher velocities, possibly due to the presence of dual vortex. Velocity is correlated with the velocity hence it increases with the escalation of flow rate. This is attributed to the large gap width, resulting in the higher internal velocities. Here is configuration of the particle tracking velocity system. Its purpose is to validate the simulation result in detecting the generate of vortex within the helix wire. We observe the frozen particles at the bottom of the helix wire to ascertain where they follow the vortex trajectory. Additionally, the Stokes number of the particles in the system is still below 1, indicating a high tracking precision. Finally, due to interference caused by the original glass tube, we switched to a liquid air interface for improved observation clarity. Under the same gap width, observing the liquid air interface at a different flow rate yields variation. is speculated that the change in internal fluid pressure in the HY caused by the flow rate alter the liquid-air interface, thereby preventing the conditions necessary for the vortex formation. Additionally, at the flow rate 100 microliters per minute, vortex formation is not observed in the actual flow field. Therefore, the visualized flow field at the flow rate of 1000 microliters per minute will be presented here. The movement of frozen particles aligns with the vortex trajectory, confirming that vortices are indeed generated in the helical wire gap as indicated by the simulation result. So, altering the gap wise exerts a great influence on the vortex morphology compared to modifying of flow rate, and the vortex shape observed for the square helix closely resembled those of the circular helix. Maintain the gap wise within the range of 90 to 150 micron was found to be crucial for substantial vortex formation. Velocity demonstrated an increase with flow rate, and the large gap wise lead to higher internal velocities. The PDB results confirm the presence of vortices in the helix wire gap as predicted by previous simulation. Thank you for watching.